Good morning, my dear student. Welcome back to this fourth session of B.Sc B.Ed integrated course, and in continuation of my earlier three lectures regarding the electrolyte conductance, today I will discuss another very important as well as very simple part of this electrolyte conductance, and that is Kohlrausch law. As you all know that it is very simple but very important law in the area of electrochemistry. And fortunately, from your school times, you are reading this Kohlrausch law, but you are the student of integrated teacher education program. That means you will become a teacher. So I will tell some fundamental aspects of the Kohlrausch law, the genesis of this Kohlrausch law, and if time permits, I will solve some of the very simple numerical problems related to that Kohlrausch law. And of course, it is part 4. Now, before I go into details of that Kohlrausch law, I must confess that I have taken some very fundamental information about these laws from a research article published in Chemistry Europe, and some of the photographs of this great scientist I have taken from that journal. As you know that this Friedrich George Kohlrausch is one of the pioneer scientists in the area of electrochemistry, because when you are studying the electrolyte conductance of large number of salts, acids and electrolytes, there is no theory. Only Ohm's law was there. And you know that time they have studied the conductance of metals and other things. But first time this great scientist studied experimentally as well as theoretically large number of electrolyte conductance and observed a very important fundamental law that is called the Kohlrausch law. And of course, he also applied Ohm's law, and successfully he has applied the Ohm's law, and that was ultimately finalized. And then of course, you know, I have already discussed the Oswald dilution law or the great Arrhenius theory of the dissociation and other things. But his contribution is, I think, in the year of 1875 to 1890, like that. And you will be very happy to see, again I have taken these photographs from this journal, as I told you, that Chemistry Europe, and there is a special series, Electrochemical Science Advances, and you will be excited to see all these great electrochemists. And as you know that this is Kohlrausch. Why I have written the 1875? Because his theory is published in 1875, and that great scientist Arrhenius, 1884, you know that I have already discussed the Arrhenius theory, and in addition to that, you of course in future will study the Nernst equation. You all know that electrochemistry Nernst is also there. Then there are some other scientists, Hellier, Arrhenius, Nernst, they are all there. So it is very, and I am really grateful to this journal chemistry Europe, I have taken these photographs to you, that because you will become a teacher, so you must tell some story of that Kohlrausch law to the student, that this is the starting point of that electrolyte dissociation and ionic conductance, molar conductance and other things. And of course, before that, there is only one law is there, that is Ohm's law. You all know these things. I have already discussed the Ohm's law. So you can say that it is they are the founder of the modern electrochemistry. And when he performed large number of experiments, on the basis of the results of those experiments, he concluded certain theory, and that is the Kohlrausch theory. Because there was a problem that how to calculate the molar conductance or equivalent conductance of the weak electrolyte at infinite dilution. And that problem was solved by the Kohlrausch. And first time he actually contributed that this molar conductance at infinite dilution comprises of the individual ions, migration of the individual. Today I will not discuss the ionic mobility and other things. That is another part, the transport number, ionic mobility. Today I will just discuss what is actually Kohlrausch law. So after this brief history, in one sentence, you can call it that it is the fundamental understanding and prediction of behavior of ions in electrolyte solutions. I think this is the first principle, fundamental understanding. And you are all aware of the definition of the electrolytes, that it is a substance that contains both cation or anions when it dissolves in a solvent, and of course it conducts the electricity. Or you can say that an electrolyte in a substance that when it dissolves in a solvent or in a molten state produce the free ions, that is cations and anions. And that of course, that conduction of electric current depends upon this movement of these cations and anions and other things. So that was the first theory. But he actually performed large number of experiments in between 1870 to 1880. And if I take any electrolytes, maybe strong or maybe weak. So you know, if I write acetic acid, or if I write univalent sodium chloride or hydrochloric, so that it dissociates. And form, like if I write sodium chloride, so it produces Na ions and chloride ions. Whereas if I take magnesium chloride, MgCl2, so it gives magnesium, of course, and 2Cl like that. So this number is very important. So, and his objective is that how to calculate the molar conductance of that electrolyte at infinite dilution. And now it is up to you. You can write like that, molar conductance. In some books it is like that, not like that. In some books you can write like that. You can write infinite like that, or n. So there is no problem. It is up to you how you represent the molar conductance at infinite dilution, or sometimes it is called the limiting molar conductivity, if I dilute the solution and other things. And so that molar conductance of the infinite dilution is the sum of, if there is two ions, sodium ions and chloride ions, so ionic conductance of, if it is nu plus, I can write like that, new number of ions is produced. So you see that ionic conductance of cation at infinite dilution of that particular ion. So the individual ion, migration of the individual ion, and ionic conductance of anions. So आप एक शब्द में बोल सकते हैं, although there are two types of forms. One is for weak electrolyte and strong electrolyte, low concentration, that at infinite dilution, molar conductance is comprises of, or sum of, ionic conductance of the cation plus ionic conductance of the anions. But of course, we have to consider the number of ions produced. That is also very important. So that is actually Kohlrausch law. Now, if you see just very carefully, you see this data so that you can understand the meaning of Kohlrausch law. Now, I have taken this data from a very good book. You can also refer that book. It is Physical Chemistry by G.M. Barrow. I am having the old edition, of course. It is 5th edition, but the recent editions are also available in our library. You can refer this book. In addition to that, आप कोई भी अंडरग्रेजुएट के जो फिजिकल केमिस्ट्री के बुक्स हैं उसको भी आप देख सकते हैं, क्योंकि जब तक आप इस डेटा को नहीं समझेंगे आप कोलरास लॉ को नहीं समझ पाएंगे. एंड फॉर्चुनेटली जब आप 4th सेमेस्टर में आएंगे तो यू हैव टू परफॉर्म दिस एक्सपेरिमेंट, एंड इट इज वेरी सिंपल दैट यू शुड टेक 1 or 2 electrolytes, maybe strong, maybe weak, and measure their observed conductance, specific conductance, and equivalent conductance. And then I will ask you that determine the molar conductance of solutions at infinite dilution, molar conductance of that electrolyte. So मैं आपको यहाँ पे example दिखा रहा हूँ. I have taken deliberately some strong, ये ऐसा लिखा जाना चाहिए, CH3, ये देखिए CH3COO, थोड़ा टाइपिंग में ऐसा आ गया होगा. Then it is a weak electrolyte, you know. Then I have taken potassium chloride, sodium chloride, and hydrochloric acid, HCl, very strong electrolyte. And in addition to that, I can take copper sulfate also, CuSO4. Okay. Different, I have prepared different solutions. उसको अलग अलग विलायन सोल्यूशन बनाया, 1 molar, 0.1 molar, 0.01 molar, 0.001, 0.0, and infinite dilution. We just assume. I want to see the effect of dilution. आपने इसको डाइल्यूट करते गए एकदम इन्फिनाइट, जब तक आप पूरा कंप्लीट डिसॉल्व हो गया, एंड मॉनिटर देयर or calculate their equivalent conductance or molar conductance. Now bear in mind, because here it is 25 degrees centigrade. Most important thing is that please see carefully the units, क्योंकि आप जब बुक्स देखेंगे या एक्सपेरिमेंट करेंगे, आप लोग स्कूल से अभी B.Sc में आए हैं, इंटीग्रेटेड यू आर टीचिंग इन द यूनिवर्सिटी टीचिंग डिपार्टमेंट, सो यू मस्ट नो द यूनिट्स, कन्वर्शन ऑफ द यूनिट्स एंड अदर, दिस इज वेरी इंपॉर्टेंट. Here I am using the SI unit, Siemens meter square per mole. You can also write centimeter squares, Siemens centimeter square. So you have to convert this. How to, you know, how to, 1 meter is equal to how many centimeters? So 1 meter square is equal to 10 to the power 4 centimeter square. So you can convert it. आप उसको कन्वर्ट. बट व्हाट इज इंपॉर्टेंट, इफ यू सी द एसिटिक एसिड एंड इफ यू सी द वैल्यू वेरी केयरफुली, जस्ट आप अच्छे से देखिए, अगर मैं इसको सीमन सेंटीमीटर स्क्वायर में कन्वर्ट कर दूंगा तो ये होगा 163. Siemens centimeter square mole per mole. Then 492, then 677, and I think no 16, then 49, 67, and 390. So there is a drastic change in infinite dilution. There is a drastic change. But if you see the potassium chloride, if I convert it into the centimeter square, so it is suppose 111, then 128, then 141, then 146, 147, 149, or if you in the language of meter square. So the trend is not very drastic change. That means if I dilute the solution, the molar conductance at infinite, this is gradually increasing, you see. But in higher concentration, it is decreasing like that. So by extrapolation method, I can calculate the मोलर कंडक्टेंस एट इनफाइनाइट डाइल्यूशन. हम इसको मान के चल रहे हैं कि ये 149 इज दैट इनफाइनाइट 149. देन आई हैव टेकन सोडियम क्लोराइड which is also strong electrolyte. So 106, 0.00118, 0.0127, 0.0124, 126. So again, trend is normal trend. Now if you see the hydrochloric acid, which is strong in comparison to KCl, and so it means that ions plays a very significant role. Here you see, if you see the magnitude, if it is 0.119 Siemens meter square mole inverse 1, where it is 0.332 in terms of centimeter square, 119,332, very high. So naturally it conducts the electricity very fast. So the movement migration is different here. But if I take another compound, magnesium chloride or sodium chloride or sodium sulfate, so the contribution of the sodium will be same. Of course, the concentration is very important. So if I plot a graph between here, I can, or if I can take some blackboard, just yes, color. So if I plot a graph, molar conductance and under root of C. Under root of C. Of course, unit you know that moles per liter DNQ, half like that. So I am getting different types of plots. So for example, it is of course suppose this is 400. Suppose this is 300. That time 200, 100, of course in centimeter square. So if it is a hydrochloric acid, you will see just like this. Now trends is hydrochloric acid. Then if I take KCl, like that, KCl. If I take acetic acid, like that, acetic acid. So you see the nature is different. And if I take copper sulfate, another electrolyte, it is in between like that, it is also like that, like that. And my problem is that I have to calculate the molar conductance at infinite dilution. So by extrapolation method I can calculate it. I can calculate it. But for acetic acid, you see the system. Here it is also very difficult to extrapolation. How do I extrapolate this? So question arises that how do we calculate the molar conductance of weak electrolyte at infinite dilution? You can ask me, sir, why the nature of copper sulfate is different? Today I will not discuss about these things, but you must know that it is due to ion pairing and hydrochloric acid migrations and other things. So that is the starting point of that. That means if I want to calculate the ionic conductance of the acetic acid or limiting molar conductance, I have to add acetate ion as well as the ionic conductance of the hydrogen ion. If I add these things, I will get the ionic molar conductance of acetic acid at infinite dilution. You see here. So two trends, one is weak electrolyte, another is the strong electrolyte. So now on the basis of this observation, Kohlrausch proposed two laws. Basically, you can, if you see the most of the books, this is the actual law. Again, I am taking same thing, don't get confused. You can call it as a molar conductance at infinite dilution or limiting conducting values. Same thing, limiting molar conductivity. I have written here, separately I have written here. You can understand these things. Capital lambda is, you can subscript molar, infinite, or even in some books it is written like that. So there is no problem. So, and if you want to check it, you have to, sometimes you have to give the reference, because you are teaching in the university teaching department. So I am giving some good books like Atkins Physical Chemistry or G.M. Barrow or Physical Chemistry by Levine. You can get all those information like that. So in a nutshell, summarize that this lambda infinite, or you can call it is a greater is equal to ionic conductance anion, ionic conductance of cation. But again there is another rules for the strong electrolyte which is also very important, that there is a linear relationship between the molar conductance under root of C, because you have seen that graph. I have already seen that graph. You have already seen that graph. Molar conductance is a linear relationship. Of course, it is for strong electrolytes. We have already seen. So that formula is also there, that molar conductance at infinite dilution, K is called the Kohlrausch constant, because when you plot a graph between the molar conductance and under root, so there must be some slope y is equal to mx plus c. So that is called the Kohlrausch constant, which depends upon mainly on the stoichiometry of the electrolyte. That when I will solve some problem, आपको समझ में आ जाएगा कि stoichiometry क्यों important है. Number of ions, if it is a univalent ions, sodium chloride, KCl, so there is no problem. You can directly write the ionic conductance of sodium, ionic conductance of chloride, ionic conductance of potassium, ionic conductance of chloride. But अगर आपने मैग्नीशियम सल्फेट लिया या मैग्नीशियम क्लोराइड, 2 क्लोराइड आयंस इज प्रोड्यूस, सो उसके इक्वेशन अलग हो जाएगा. So now that is the actually theory. And if you ask me, sir, actually he discovered this thing in the year of 1875 to 1879, and this Kohlrausch square root law, it is actually discovered in 1900, because that concept, the role of ionic conductance or the molar conductance, equivalent conductance, was discovered by the Debye-Huckel-Onsager equation. बिकॉज इट इज ए टेक्नोलॉजिकल एडवांसमेंट. आप धीरे धीरे पढ़ रहे हैं, इसके बाद आप पढ़ेंगे स्ट्रॉन्ग इलेक्ट्रोलाइट्स, ट्रांसपोर्ट नंबर, माइग्रेशन ऑफ आयंस, तब आपको समझ में आएगा कि व्हाट इज द एक्चुअल रोल ऑफ Debye-Huckel equation. Then we are able to explain this behavior. But today I am only discussing the Kohlrausch law. So just for student curiosity, the first law, the simple law, ionic conductance of cation, ionic conductance of anion, is called Kohlrausch law on the independent migrating ions, because the contribution independent ions. And the square root law, this is called the Kohlrausch square root law. Reference Atkins or Levine or any other books, you can refer it. So now अब आपके मन में प्रश्न आना चाहिए कि why, जब हम if I increase the concentration strongly, why there is a decrease in conductivity, equivalent conductivity? Because you know that when there is a increase the concentration, ions pass आ जाएंगे. You see that when the solution is more concentrated, the ions come close together, so there must be electrostatic sometimes attraction or electrostatic repulsion. So it is very difficult for the ions to move, उनकी movement कम हो जाएगा, because they are close, they attract or repel each other, which slow down their movement. And electrical conductivity depends upon the movement, ionic mobility. So therefore that is decreases. And since the ions move more slowly, the solution conducts less electricity. But if we take the weak electrolytes, you know that it depends upon the degree of dissociation. So I am just again same thing. Now you can understand these things. A, B, this is A and B like that. So it is the contribution of each ions, cation and anion. Now I am coming to the how do we calculate the equivalent conductance at infinite dilutions. Now again these values are available in the books, internet, undergraduate books, everywhere you will get it, and you have to just sum it. Say for example, here again and again, मैं जो आपको बार बार बता रहा हूँ, यूनिट्स में स्टूडेंट कंफ्यूज हो जाते हैं. तो मैं यहाँ पे जो लिखा हूँ वो मैं CGS यूनिट में लिखा हूँ. जैसा जो आयोनिक कंडक्टेंस एट इन्फिनाइट डायल्यूशन, इट इज सीमेंस सेंटीमीटर स्क्वायर मोल इनवर्स 1. If you want to convert it into meter square, so you know that 1 centimeter is equal to 10 to the power minus 2 meter. But meter square means 1 centimeter square is equal to 10 to the power minus 4 meter square. So here suppose I am giving the example of hydrogen ion. So ionic conductance at infinite dilution is 349.83. आप उसको सिग्निफिकेंट फिगर्स में भी लिख सकते हैं, 349.8. सिमिलरली आयोनिक कंडक्टेंस ऑफ OH आयन, अगेन इन सेंटीमीटर स्क्वायर 198.6. अगर इसको आप मीटर स्क्वायर में लिखना चाहेंगे तो 198 इंटू 10 टू द पावर माइनस 4, 198 10 to the power minus 4. Similarly, sodium ions is 50.11 like that. Potassium ion 73 approximately. Lithium like that. These are all available in the books. Sulfate, ये टाइपिंग मिस्टेक हुआ होगा, देखिए सल्फेट टू ऐसा ऐसा भी लिख सकते हैं और सल्फेट टू नेगेटिव ऐसा भी आप लिख सकते हैं. अब मैं छोटा सा सिंपल क्वेश्चन स्कूल लेवल से आप पढ़ रहे हैं. सपोज आई एम गिविंग यू द आयोनिक कंडक्टेंस or limiting conductance at infinite dilution of acetate ion and ionic conductance of hydrogen ion. So what would be the equivalent conductance or molar conductance of acetic acid at infinite dilution? आपको एक्सट्रापोलेशन की जरूरत नहीं है. हमने क्या किया, ये एसीटेट आयन का 349.83 एंड हाइड्रोजन आयन का है 40.9. Sorry, hydrogen ion, acetate ion is 40.9 and hydrogen ion is 349.83. I दोनों को जोड़ दिया and I'll get 390.73. So that is the equivalent or molar conductance of acetic acid at infinite dilution. Similarly, अगर आप सोडियम क्लोराइड का देखना चाहेंगे, पोटेशियम क्लोराइड का देखना चाहेंगे तो 73 plus 76 around 150 or like that. So you can get it. ये देखिए जैसे KCl का अराउंड like 149 like that. बट उसमें स्ट्रॉन्ग इलेक्ट्रोलाइट में एक्सट्रापोलेशन से निकाल सकते हैं, लेकिन वीक इलेक्ट्रोलाइट के लिए आपको उसको कैलकुलेट करना चाहिए. नाउ द लास्ट पार्ट, आई थिंक यू हैव now you know the formula of the Kohlrausch law. It is very simple. Now I am giving a very one example, and I suggest all the students, there are a large number of good books are available in library, and there is a book Physical Chemistry Through Problems by Dogra and Dogra. So there are a large number of numerical problems related to the Kohlrausch law. So you should solve at least 5 numerical problems. Here I am giving one example. So for example, calculation of molar conductance of sodium chloride at infinite dilution. It is a simple, no complicated mathematics or science is involved. So they have given the ionic conductance of sodium is 50.1, 76.3. Again I am using the CGS unit just for easy, centimeter square. So I have to add it. Ionic conductance of sodium, ionic conductance of chloride at infinite dilution or limiting conducting value. You just add it 50.1, 76.3. Answer is 126.46 centimeter Siemens square mole. Sometimes the examiner may check your IQ. So they may be asked that convert it into meter square SI unit. Then you have to convert it centimeter square to meter square like that. Second problem, same thing, but here question is in place of magnesium chloride. I have circled. So again same thing, ionic conductance of infinite dilution or zero, ionic conductance of magnesium. Now you must be very careful because there are twice ionic conductance of chloride. So you see magnesium is 106, ionic conductance is 76.3. So there is no problem, magnesium is 106, but here because 2 chloride ions is there, stoichiometry. So 2 multiplied by the ionic conductance 76.3. So total value is 258.6 Siemens centimeter square per mole. As I told you just few minutes ago that you convert it into. So you know how to convert the meter square to centimeter square or centimeter square to meter square. So just in terms of SI unit, it is Siemens, not par actually, it is just not par, centimeter square like that. Not, it is just like Siemens, Siemens centimeter square, like that, simple. Siemens centimeter square per mole, that is the unit, or Siemens meter square per mole. Just like that. Siemens, just convert it meter square. Now the last question. Sometimes what happened, they have given you 3 compound. Calculation of the molar conductance at infinite dilution of the acetic acid. Using, they have given the molar conductance of 3 electrolytes. Maybe some weak, maybe some strong. Very simple algebra like that. They have given the sodium chloride, hydrochloric acid and sodium acetate. So, how do I calculate these things? That means if I take hydrochloric acid, so it converted into lambda of H plus lambda of Cl. Then we add sodium acetate, lambda of CH3COO plus lambda of Na minus lambda of sodium minus lambda of chloride. So you know it is a very simple thing that this sodium, this chloride, this chloride. So what I am getting, the CH3COH. So such type of numerical problem may also be asked. So here you see there. Here actually it is CH3COH. So CH3COH value is suppose 426. HCl is 426 plus sodium acetate is 91 minus sodium chloride 126.4. So your answer is 390.6 Siemens centimeter square per mole. So similarly, large number of numerical problems are available. So I will not go into details of this question, but you can solve it with the help of good books. Now last, of course, as we have seen that it is a very old equation because he is one of the pioneer in the area. You just imagine 1875 to 1880 or 1890. There was no laws were there except the Ohm's law, and this law is applicable for the, of course, of infinite dilution, because that is the rules, no alternative is there. And at higher concentration, as you see that when I have seen you the copper sulfate, because that is not like that there is only ionization, there may be some others, ion pairing, and there are some other ion pairing and other things is also there. Ion-ion interaction is also there. Then you know the relaxation effect, electrophoretic effect, and that problem is of course solved by the great scientists. Therefore, it is called the extension. Extension of such theory is called the Debye-Huckel-Onsager theory, which was proposed in 1927. You can just imagine this thing, and that is also in your course. So in future we will study this Debye-Huckel theory. Then sometimes they ask some application of the Kohlrausch law. There are a large number of applications, and I can say to the student that actually the validation of different ionic theories of electrochemistry, whether it is Arrhenius or Ostwald dilution law, Debye-Huckel theory, ionic mobility, transport numbers, all are based on the results, theoretical and experimental results derived or given by the Kohlrausch. So, and of course, the most important application is the determination of molar conductivity at infinite dilution for weak electrolytes. It's the most important application. Then of course the calculation of degree of dissociation, because you know that if I want to calculate the degree of dissociation, so I need the equivalent conductance or molar conductance at infinite dilution. So how do I calculate unless until we know the values of infinite dilution? So that can be calculated with the help of Kohlrausch law. Then of course ionic mobility and transport number starting point with the help of this Kohlrausch law, the results of the Kohlrausch law. In the next class I will discuss the transport number and the ionic mobility. And then of course the determination of the solubility and solubility product, because if you take the sparingly soluble salt like barium sulfate or lead sulfate, so complete ionization is not possible. So just let me summarize that today I have discussed very briefly the theory of Kohlrausch law, and I have tried to explain the genesis of the Kohlrausch law, and I have also explained the application of the Kohlrausch law. I have solved very fundamental, very easy school level numerical problems. I have also shown you the complete tables of that various values of molar conductance of strong electrolyte, weak electrolyte. So on the basis of this, I think now you are able to understand completely the Kohlrausch theory. In my next class, I think I would like to discuss the transport number or the ionic mobility, which is of course related to the Arrhenius theory. And of course then for the strong electrolyte, the Debye-Huckel and Hunsaker theory is very important. So this will cover whole course of your B.Sc, B.Ed, I think third semester chemistry, some part of course physical chemistry, electrochemistry. Thank you very much.